We are back on coupled oscillators, and we have a lot of work to do, and I'm probably going to make a mistake. But mistakes are just a part of life, right? So in the last video, we looked at two masses connected by three springs. And in that case, that spring and that spring was the same. The two masses were equal. The middle spring could be different. We didn't really care. And we found the normal modes, and we didn't do anything super crazy. But what if, although those things are different, unequal masses, unequal springs, how do I find the normal modes? Do the normal modes even exist? And that's what we're going to do. There's some work to do, and it's a little strange, but we got it. Okay, so the first thing we can do is to write down equations of motion using Newton's second law for the two masses, right? Because still F net equals mass times acceleration. That's still true, and both of the springs only have two forces, so it shouldn't be too bad. If we start with mass 1, I can say mass 1 times, oh, and I'm going to call this x1, and I'm going to call that x2. Okay, so x1 is the distance that x1 moves in the positive direction, and that's in the positive direction too. So those are my two variables. And then when I say x1 double dot, right, that's the acceleration, right? So dot notation means derivative with respect to time. Hope you're okay with that. We're going to move on. Now, what forces act on this mass? Well, the first one is this spring right here. So if this moves in the positive direction, I'm going to get a negative k1 x1, right? Because if it moves that bit, then it's going to stretch. Now, this is where I always make mistakes, but we got it. We're going to do it. Now, this spring also exerts a force on it. If the mass moves that way, we're going to get a negative spring force. So negative k2 times x1. But if that mass moves that way, it's going to make it stretch and actually pull it in the positive direction. So I actually need this x1 minus x2. And I did that in the last video too. So if that's a little wonky for you, I'll link that video down below and you can do that. So that's my equation of motion for the first mass, and we can make that simpler in just a second. Now if I look at mass 2, I have mass 2 is x2 double dot, and that's going to be, now let's do the same thing. I'm going to go over here. If this mass moves that way, the spring's going to push that way. So I have minus k3 times x2. And then we can do the same thing over here. It's just going to be backwards from this, right? So I'm going to get minus k2, and I'm going to switch the order, x2 minus x1. So that's my two equations of motion. Now, let's take a moment and model this for some just random situation of masses and springs in numerical calculations. So if I can calculate, if I know the position of all these masses and their initial velocities, then I can calculate the acceleration for mass 1. I can calculate the acceleration for mass 2. It's just an equation. And then by breaking this into delta t of 0.01 seconds, I can calculate the acceleration, x1 double dot, calculate the acceleration, x2 double dot. Now I can update the velocity. And I apologize if I'm going through this fast, but I've done this a bunch of times. So I'm going to call this x12 dot is x11 dot plus x1 double dot delta t. So this is the velocity, x dot, at the beginning of the time interval, and that's at the end of the time interval, and that's the acceleration. And then I can do the same thing with the position, x12, so it's 1 at the end, 1 at the end, is x11 plus x12 dot delta t. And then do the same thing for mass 2. And I've already done this, I didn't program it in, because I wanted to make an animation. It takes a long time to put that stuff together. If you really want to see the animation, let me know how to make the code. I will show you the code. I will give you the code, but I'm just going to show you the code and run it right now. So all of these are different masses, so it's not easy. We can't do the same trick of adding these things together, but we can do it numerically very easily. It's no big deal. It's really no big deal. Switching over to Python, here is the code. So just so you know what it looks like, I have these cars and springs. I want to make everything look animated and nice for you. And then I have the spring constant. You see here that nothing's the same. K1, K2, K3, M1, M2, everything's different. So let's just run this and see what happens. And I plot the position and everything. But most importantly, we want to see the animation. So there's my two masses. They're moving back and forth in some manner. If you set them up with initial positions and velocities, they don't have the same normal modes because that trick only worked then, right? That was the point. And there's the two position graphs. But we want to find normal modes, and we can find normal modes, and we're going to find normal modes. Okay, so let's go back over here and see how would we possibly find normal modes. The first thing I want to do is to rewrite these two equations. Because, you know, there's something where I know how it works, right? So it's not like I'm just doing this randomly. I already know how this works. So I'm going to write this equation right here, m1 x1 double dot. Now I want to get all the x1 terms and then all the x2 terms. So here I'm going to say this is negative k1. So I have a k1 and then I have a negative k2. k1 plus k2 x1, right? Because that's negative k1 minus k2. They both have an x1. And now I have my x2 term is going to be plus k2 x2. Now for the next one, I get m2 x2 double dot. It's going to be equal to, now I only have one x1 term, so it's going to be plus k2 x1. And then over here, I'm going to get minus k2 plus k3 x2. And so you see I have x1s, I have x2s. But I already know, and let's go ahead and divide, because we're going to do this later. So I'm going to go ahead and divide by the masses, which you don't actually have to do. m1, m1, m2, m2. Now, these we saw in the last video that you can get a solution for these two things. You can get them, and they were a trig function. It's still going to oscillate as some type of sum of trig functions. But the question is, what's the initial amplitude that would make it into a normal mode? So this is the trick that really got me initially. Let's say that x1, I'm going to write x1 as some constant a1 times e to the negative I omega t. Is that a solution to this kind of equation right here? Well, we already said that it was. We did that before, right? We saw that we have sines and cosines. So in that case, let's just double check. If I take x1 dot, that's going to be negative I omega a1 e to the negative I omega t. x1 double dot is going to be negative omega squared a1 e to the minus I omega t. So I'm going to get that negative omega squared term in there. Okay. Now what do? Well, I can rewrite this whole equation. I'm just going to write both of these equations using x1. And for x2, I'm going to say x2 is some other constant a2 e to the minus I omega t. So I can rewrite these two equations using that format. And I'm trying to think where I'm going to do that. What if I just erase all that and do it up top? That way I won't have to. You always have to think about, you know, what's your next move going to be and how you're going to arrange it. So right here, x1 double dot, I'm going to write this as negative omega squared a1 e to the minus I omega t. That's that. Right here, I have an x1 term. So this is going to be equal to negative k1 plus k2. Can you see that? Yeah. k1 plus k2, that's a k2, over m1. And then I have x1 is going to be equal to a1. I'm going to go ahead and factor out. Both of these terms are going to have e to the negative I omega t. So I'm going to just factor that out. So I'm going to put a parenthesis right there. And I'm going to say plus a2, because I have x2, a2 k2 over m1, and that's going to be e to the minus I omega t. So that's the same thing as this, right? All I did was substitute in this new form right there. Now let's rewrite the other one, negative omega squared a2 e to the minus I omega t is going to be equal to, right here, oh, I should put that one at the other end, k2 over m2 a1 minus k2 plus k3 over m2 a2, and that's going to have that e to the minus I omega t term. But now, look what happened. Because of that choice of our solution, I can divide both sides by this exponential term, and that's just gone. So I don't have to rewrite it because I have an eraser, right? So I can just erase it. And through the magic of eraserhood, I can do a couple things. I can divide both sides by negative omega. I'm going to divide both sides by negative, just negative. I'm going to leave the omega squared over here. So let's do that. Or multiply, so that's going to be plus, that's going to be minus, that's going to be minus, that's going to be plus. And then, I can't really factor out the a1, a2. I can't factor out the a1, a2, but I can write this as a vector operation, a vector multiplied by a matrix. And we do this in linear algebra all the time, right? So let's rewrite this as the following. Omega squared times the vector a1, a2 is equal to a matrix, and that matrix is going to be equal to k1 plus k2 over m1 minus k2 over m1 minus k2 over m2 plus k2 plus k3 over m2. All of that times the vector a1, a2. And you could just check, right? And you should check this, right? If I take this vector and operate here, I get an a1, I get an a2, and then I get an a1, I get an a2, and that's equal to a1 and a2. So I get two equations. So I can write that as this vector operation. And maybe you see the magic here, right? Because this is a very important equation in physics that we see, and it's the eigenvalue equation. Because what we have is a matrix operating on a vector, and we get that same vector back with a scalar. So we operate a vector, we operate a matrix on a vector, and then we get the same vector back. That is the eigenvalue problem. You could write this as omega squared, what did we call this vector A? I guess I could call that the A vector. I can't remember what I did. And we'll call this the K matrix, capital K, A. So I operate K on A, and I get A back with the constant. Now, how do you solve that problem? It involves multiplying this by the identity matrix, subtracting this from both sides, and so you get this weird matrix determination where you're going to get this minus omega squared, this minus omega squared, and then you take the determinant to show that's equal to 0. Nobody wants to do that. You should do it at least once, and hopefully you have done it at least once. But even for a 2 by 2 matrix, it's like, don't want to do that. It's just algebra, it's just these numbers. But then I have all these different values, and I'm going to get a quadratic equation because I have a square matrix, and I just don't want to do it. So I'm not going to do it. Okay, so instead, I'm going to show you how to solve the eigenvalue problem, which means what are the values of A1 and A2 that work, and what's the values for omega that I get for that. So we actually get two things. And I'm going to show you how to do that in real Python. And then what we can do is to use our values and go back to our animation and see if we do get normal modes. Because these are the normal modes that we're solving for, right? These are the modes where I operate and I get the same thing back, because that's what I assumed. So let me show you how to do this in real Python. And let's just jump over and do it. So the first thing I'm going to do is to switch. So we are here. And I want to use the same values for K, M, and everything. So I'm going to edit this code. I'm just going to copy this. OK. Now, up here, I already have real Python. So if you have not installed real Python, that's cool. You can use Google Colab. Google Colab's an online Python that has all this stuff in there, so it's pretty good. So the first thing I'm going to do is to import the NumPy module. So import NumPy as NP, and then I'm just going to run that. So Shift Enter will run that cell. So if you're not familiar with real Python, it's fine, but we break everything into these cells. You don't have to, but we do, and it allows us to rerun different cells. You can put in code and mark down text and equations. It's super nice. I just don't really use it that much. But now I'm going to go ahead and define, I'm just going to paste my values there. Okay. The next thing I need to do is to make my matrix K, right? Because that matrix, that's what I want to find the eigenvalues for. So I need that matrix right there. So in Python, we can make a matrix as an array of arrays. So I'm going to make an array, a two by two, a two list array, and a two list array, and that's going to be my matrix. Okay. And then I'm going to use the variables K1, M1, K2, M2, K3. So if I want to change those, I can. I'm going to use this as capital K, just like I said before. And it's going to be equal to np.array. So an array is a function in WebVPython. I mean, not WebVPython, in NumPy. Okay, so I had to call it from NumPy. And now I'm just going to say bracket, and I'm going to start entering my thing. So I have K1 plus K2 over M1. K1 plus K2 divided by M1. Now the next term is going to be negative K2 divided by M1. And that's my first row. And then my next row is going to be equal to comma. You see how I'm doing there? Negative K2 over M2, negative K2 divided by M2, comma, K2 plus K3 divided by M2, and that's my K matrix. I always print this out, print K, because you never know if it's going to run or not, and you just want to check it. Okay, so and note it that these are just numbers now, because WebVPython, not WebVPython, real Python, we're dealing with numbers here. NumPy deals with numbers. Num stands for number. Okay. Now I can go ahead and find the eigenvalue and the eigenvectors for this. It's super easy. There's a built-in function called eig. And so let's just do the following. I'm going to say W2, comma A, because I'm going to get both the solutions back. I'm going to get the eigenvalues, omega squared, and the eigenvectors A. So I'm going to set both of those equal to what I'm doing. And it's np.linearalgebra, so lin alg dot eig, and that gives me the eigenvectors, but then I have to give it the matrix that I want to, so K. That's it. And I'm going to print, let's print np, let's print like this, W equals, these are our angular, these are going to be the normal mode angular frequencies, np dot square root of W2. So I should get two of them. I think that'll work. Yeah, so they're my two angular frequencies in this situation, which seems kind of high, but I'm going to go with it. Now, what about my eigenvectors? And these are going to be my initial amplitudes for the two masses. And notice I didn't have a phase shift or anything like that, because in my x equals a1 e to the negative I omega t, because I'm assuming they start from rest. So I can get those, I already calculated them. But if I just print A, I just want to show you what it looks like. It's a series of numbers, right? So this column is A1 and this column is A2. But I want to print it out as I want to take the transpose of that and rotate it. So let's print, I'm just going to print A dot T 0. So that's going to be, I'm going to take the transpose, I'm going to take the first row, and then I'll do the next one, print A dot T the second row. And so those are my two initial values. Now, those are normalized eigenvectors. All right, so if I put in my values of 0.9 and negative 0.3 or whatever for my initial positions of my masses, it's gonna be crazy weird because the amplitudes are so high. So I can multiply that by any factor that I want, and that's what we're gonna do. So let's just copy these two and then switch over to WebVPython. Go over here to WebVPython. Is this it? Yep. And I'm going to just here I have x1 and x2. Those are my initial positions. I had 0.3 and 0.03 and so let's put this as a comment so I won't forget it. So I want to put them as these two values. So I mean, I could just multiply by 0.3, and that's what I'm going to do right now. So I'm going to take this number and multiply it by 0.3. And then I'm going to take this number and multiply by this right here, negative. And let's see if we get a normal mode. And it may not work, because you never know if things are going to work or not work. Well, let's just try. Now, you may think, okay, that doesn't quite look like a normal mode, but it is a normal mode. They don't have to have the same amplitude of oscillation. They have to have the same frequency of oscillation. Let's switch down to the graph and see what the graph looks like. You can see those are both oscillating trig functions. Those are simple harmonic oscillators. They have different amplitudes, but they have the same frequency. In this case, but they're moving in opposite directions. Let's go ahead and plug in the other normal mode and see if that one works too. So I'm going to switch back over here to my real Python. I'm going to copy that. And this is barbaric. You think it's barbaric to copy and paste? You can do it all in WebVPython, you fool. Yes, I can, but I don't want to. Okay. I don't like running WebVPython in or VPython in normal Python because it gets a little weird sometimes. So let's just multiply this and change that one, and then this for this, and then run it. Normal mode. Okay, so they're still oscillating with the same frequency in the same direction, right? You can see that. But they don't have to have the same amplitude, just like before. So, but it is a normal mode. Normal mode. Two normal modes. Using the eigenvalue problem. And that's what's really cool. Now, can you do this for 3 masses and 4 springs? Yes. But again, you're going to get a 3x3 matrix, and so nobody wants to take the determinant of a 3x3 matrix. I promise you that. Nobody wants to do it. So maybe I'll show you how to do 3 masses. But you know, the cool thing is you could do anything. There's a classic, let me show you the classic case of, I'm going to do it real quick. So let's just destroy this code. So what if this spring is gone? Will there still be normal modes? And the answer is yes, there will be. So let's delete that spring. It's going to take a little bit of work. Should I even do it? I'm going to do it. Okay. So K3, I'm going to put it at 0. So I don't have to change the code, right? But what I do need to do is I need to remove that spring. So I'm just going to get rid of that spring. I'm not going to display it. And then down here, I'm going to get rid of this because I don't want to display that. And that should do it. So we should have the same thing happening. It will not be a normal mode because I've adjusted the spring constant. I made it 0. Let's just see what happens. So not a normal mode, you see. Not normal. You see that's not a simple harmonic oscillator. But now if I go back over to my real Python, I can calculate that. So over here, I'm just going to go up here and change K3 to 0. I'm going to rerun this cell. I'm going to rerun this cell. I'm going to rerun this cell. I'm going to well, I didn't need to do that one. I'm going to do that. So now I have different normal modes. Let's just copy this one right here and see if we can get this to work. So going back to WebVPython, now I'm going to give them a different initial positions. Where did that go? Oh, it's up here. Let's just put it as a comment because you know I'm going to forget. So I'm going to copy this for x1, paste, copy this for x2, paste, and run it. I'm kind of scared. I don't know if it's going to work. Okay, I mean, looks worky. And there. You can see from the position graphs, and I did shift these up so that we can see them. Those are both simple harmonic oscillator graphs, right? So that did indeed work, and that's kind of awesome. Okay, so I'll put a link to the previous video down below. I'll give you this Python code. I'll try to put the spring back so that you can build that. The visualization is really important, right? And this is in 3D, remember that. And then you can play around with, you can make your own springs and try it yourself. But you will have to enter your own code into Google Colab. So that's that. But it's pretty easy, right? All right, the end. Talk to you later.